systems and its relationship to the peak luminosity obtained from high-speed video cameras. And it's just the preliminary results with an emphasis on preliminary. Okay, so I'm going to talk about PyRAW, which is a tool we are developing to make this kind of analysis. I'm going to present very briefly the events that we chose for this preliminary analysis, some of the obtained correlations, the preliminary conclusions, and the future work that we are planning to do in the next month. Okay, talking about PyRAW. It's a Python library that we are developing, some of the authors are developing since March 2013. So it's very recent. It's still in the first versions of it. And it's aimed at reading and manipulating raw image files for a wide range of lighting analysis and research. So what does a raw file look like? So this is one frame. Okay. This is one frame of one of the events that we analyzed. It's visualization made by the commercial software of the high-speed camera manufacturer. But if you look at the raw data, this small area here looks like a whole bunch of numbers. It's one pixel value for each of the pixels of the CMOS data that the camera recorded. And if we look further, so you can see one value for each one of the pixels. So it has 1,200 horizontal pixels and 500 vertical pixels. So the current functionalities of this library are the false color visualization, image background removal, and luminosity versus time curves. So this is how we would usually see the monochromatic typical lighting record provided by one of the cameras. And this is the false color imagery that we can generate with PyRAW. You can see that the levels of gray here to the eye, they are very, very subtle. But here you can see a large difference between, like, for example, the luminosity spread here to the luminosity spread here, which is less intense than the one in the main trunk of the channel. And here you can barely see the difference. So especially for faint events, this is a very powerful tool for manual analysis that a researcher could do on the video records. So this is a closer look at both images. So you can see a large number of colored levels until you get to the main channel. This is another case which is less intense. So here you can see mostly only the main part of the channel, and when you go to the false color imagery, you can see the scattering of light around the main channel more easily, and you can see in these red regions where it gets more intense. And we can also remove the background from the images, which can be helpful for some of the analysis. So this is one frame of background, and the software goes after 10 non-consecutive background images and make an average background image for a single video. And then we can remove it from any stroke or other process that you want to analyze in detail. So here's that first more intense return stroke. So you can still see a lot of light scattering in the surroundings of the channel. But when you go to less intense cases, it looks like a more promising feature, because most of the background is completely removed, except for these dots here that later we found out it was traffic for one of the bridges that crosses the river over here. And for now, we can also get luminosity versus time curves for a rectangular area that the user can choose in the video. And this is for one of the bipolar events that Antonio Saraiva mentioned in his earlier presentation. This is for the other bipolar event that I'm going to talk about in the next section. So going to the analyzed events. We chose two bipolar flashes that were recorded on March 13th, 2012 by one of the Ramer stations. It was during the Chuva same thing. They were chosen because there were no saturated pixels at the return stroke frames. Resolution, 1200 pixels by 504 pixels. It was recording at to 2500 frames per second with 390 microsecond exposure time in an 8-bit pixel depth, which means we had 256 levels of gray. So this is the first event, the initial positive stroke, and 4 subsequent negative strokes. And this is the second case that we're going to focus on this presentation today. I don't show the initial positive stroke. It was further to the right, followed a different path from the 15 negative strokes. And these are strokes number 1, 3, 7, 9, and 11. So a general time overview of case 2. Here we have the first negative stroke, the first positive stroke, excuse me. The first negative stroke, there's a bit of confusion between the networks that we are discussing in another paper, but we can talk about it later if you wish. Then these are the undetected strokes, and these are some of the negative strokes that were detected by BrazilDAT. So going to the correlations, which is the main objective of this presentation, regarding only BrazilDAT, this is the estimated peak current and the luminosity given by the Pyrrole analysis. We get this linear correlation here with an R squared of 0.72, which is fair. Not that good, but we can say that there's a correlation between the two parameters. If you go to LINET, the R squared drops a little to 0.51. We can see they are, to the eye, they look very similar with this outlier, the more intense stroke, a bit far away from the main curve. But when you go to the other networks, TLS 200, the R squared falls a little further to 0.45. And we can see there's some spreading over here that is pretty far from the adjusted curve. And when we go to GLD 360, things get even worse. And the R squared drops to 0.27. But the BrazilDAT underestimates the peak currents by a factor of roughly 2. If we compare BrazilDAT to TLS 200, again we have a very high R squared, and now the factor is about 1.76 with some linear correction as well. BrazilDAT versus GLD 360, again very high R squared, but now a higher factor of 2.49. Now, LINET and TLS 200, again, very high linear correlation, and the peaks are very close, a 0.89 factor between them. GLD 360 and TLS 200, again, this is the lowest R squared of all the correlations we made, but still it seems to be closely related, but GLD 360 seems to overestimate a little, as we have a 0.68 factor here. And finally, GLD 360 in LINET. Again, high R squared and a little lower linear factor if we compare to the LINET and TLS 200 factor. So the preliminary conclusions. BrazilDAT and LINET peak current estimates, they are positively correlated to the pixel intensities of the return strokes. But at least, well, we can say that at least for the less intense strokes, below 5 kiloamps for Brazil DAT and below 10 kiloamps for LINET. If we go further, there's that outlier that's pretty distant from the adjusted curve. But if we go to TLS 200 and GLD 360, the trend is much weaker. The R squared drops dramatically. The peak current estimates of all the networks, they are strongly correlated between each other, with R squared ranging from 0.96 to 0.99. And this suggests that the technique for channel luminosity estimates must be improved for return strokes, as we have a stronger correlation for one method for comparing network versus network. But this correlation does not appear again when we go to luminosity and networks. Then our algorithm that must be improved in some way. Going to the network versus network comparisons, we can say that Brazil DAT underestimated the analysis strokes by a factor that ranged from 1.76 to 2.49, which is very similar to, I think, what Kleber presented earlier today. And TLS 200 and LINET, they are very similar, and the refactor between them was 0.89. And overall, GLD 360 had the highest estimates. And for future work, PyRaw, has been developed for less than 2 months, so there's a lot of work to be done here. One of the main issues that we want to address is the edge detection for the lightning channel, so we can make that luminosity and intensity analysis choosing only the area that corresponds to the channel, disregarding the background or any other type of interference or noise. We also want to make this and then have an automatic area selection for those luminosity versus time curves, and also analyze and visualize the raw files that are generated by the colored cameras, which did not operate during the Chuva campaign, but we had them in the 2013 summer. And we can also compare the different color bands, red, green, blue, and see if they are different, if they are, how different, what are the main differences. And for the video analysis, we would like to look at other cases with no saturated pixels at the return stroke, preferably from the Chuva campaign, so we can have more than one lightning location system to look at, especially in terms of expanding the range of estimated peak currents. We were always for relatively low values, and see what's the effect of light scattering over those estimates. And regarding the factors between each lightning location system, we'd like to look at a larger number of events and do those plots for maybe tens or hundreds of events instead of just 5, 6, or 10, which were the case of what we have done so far. So thank you for your attention. If you have any questions.
Current estimates from the networks are the peak values, and you'll get to their peaks in different bandwidths of the sensor, and then the sensor does a calibration to adjust for its limited bandwidth, or so then find the differences of the pattern, where some of them were bigger amongst all the networks and some of them were larger. And I think it's a reflection of the difference between impulse charge and peak current.
Yeah, could be. Thank you.
Anybody else? No? All right. Have you considered to apply this technique on sprites measurements?
No.
What would expect to be it? Since,
we haven't, but if we can get the records, it would be easy to get it done. At least for a camera that can generate the raw files right away. But I think most of the current manufacturers, at least Vision Research, they have these features, so it's going to be easy to get all the curves and luminous intensity. Just a matter of getting the data. We could do it.
All right.
We could do it.
Thanks.